Bismillahirrahmanirrahim. Assalamu alaikum ji. In this video, we will talk about some of the very basic concepts related to probability theory. We will cover these concepts very briefly and very quickly. We assume that you have taken a course on probability before taking this course. So we assume that you have some prior knowledge, but in this video, I will be quickly refreshing your previous knowledge. So we'll cover some very basic concepts such as probability model, random variable, the notion of joint probability, the concept of conditional probability, what do you mean by probability mass function, what is probability density function, and so on and so forth. Okay, let's start with the concept of relative frequency. So I'm using this reference, Probability and Random Processes for Electrical and Computer Engineers by John Gubner. There are many good books about probability theory, and you can consult any of the book should you need to review the concepts in detail. Okay, so if we have an experiment that can result in m possible outcomes, O1, O2, OM, so these are the possible outcomes. So our goal here is to build a mathematical framework to represent and analyze uncertain phenomena, right? Such as rolling a die or tomorrow's weather, the result of a game between Pakistan and England. And to this end, we model the phenomena of interest as an experiment with several possibly infinite mutually exclusive outcomes, right? So we have O1, O2 to OM as the possible outcomes. We say this n subscript small n denotes the number of times the outcome OI when you conduct n trials of an experiment. We define relative frequency of the outcome OI as number of times it occurred divided by the total number of trials. When the number of trials n become large, the relative frequency converges to some limiting value, and that limiting value is what we refer to as probability. And this behavior is known as statistical regularity. Some more basic definitions. Sample space. When you conduct an experiment, set of all possible distinct outcomes is called a sample space. So one outcome of a sample space or of an experiment, we use small omega, right? And this is capital omega, which we use to refer to sample space. Events. So collection of outcomes are called events. It could be a single outcome, or it could be a collection of outcomes, and usually we denote by capital letters. Every event is obviously a subset of sample space. A couple of examples. If you roll two dice together, what is sample space? Sample space would look like this. You can have 1, 1 on both dice, or you can have any number between 1 and 6 on each die. So we have a two-dimensional sample space, discretely sampled. And an example of event could be the sum of numbers on two dice is equal to 6. For this event, so what are the possible outcomes, or what are the outcomes that are associated with this event? The sum of the numbers on two dice is equal to 6. So all of these events, all of these outcomes correspond to the event when the sum of numbers on two dice is equal to 6. Right? Another example could be a noise voltage randomly between 0 and 5 volts. So what is sample space here? Sample space is continuous in nature in this time. That is any value from 0 to 5 volts. And the event could be the noise voltage between 2 and 3 volts. So for event. So event is a subset of the sample space. So event could be from any value between 2 and 3, and sample space is any value between 0 and 5. Okay, moving towards the concept of probability model. We use probability model for mathematical modeling of the problem. A very simple model could be that you count the number of occurrences of any event and you divide by the cardinality of the sample space, right? So if each outcome is equally likely, we assign probability to the event A as cardinality of event A divided by the cardinality of sample space. And for example, if you have a fair die, and so if you want to talk about the event when the sum of two numbers is equal to 6, and if you go back, so how many, so 5 1 4 2 3 3 2 4 1 5. So in this case, probability of this event would be equal to 5 divided by 36, right? Cardinality of sample space. If you have a fair die, each outcome is equally likely. In such a case, probability of having a 1 or 2 or 3, we have mutually exclusive events, that is 1 or 6. If outcomes are not equally likely, obviously you count the number of outcomes correspond to the event, and you simply sum the number of events and divide by the cardinality of the sample space. So we use P of small omega to refer to probability of each outcome of the sample space. So for any probability model, we have some axioms of probability, some of the properties of that a probability should satisfy. Given a non-empty set sample space and a function p defined on the subset of p, we say p is a probability measure if the following 4 axioms are satisfied. The empty set is called an impossible event. That means probability of having an empty set is equal to 0. Or empty set is mapped by the probability model to 0. For any event that is a subset of sample space, probability of the event is greater than or equal to 0. If we have A1, A2, and the events are mutually exclusive, we have such that, okay, what do you mean by mutually exclusive events? That they are not sharing any value. So that means the intersection is an empty set. So, and probability of union of such events, or probability of when event A or event P or event 2 and so on, that is equivalent to probability of event A1 and A2 and A3. So since they are mutually exclusive, so we can have the total probability as sum of individual probabilities of the events. And finally, we note that probability of a sample space is equal to 1, or in other words, sample space is a sure event. We also note the monotonicity property of the probability. If we have a set event A, which is a subset of event B, probability of A would be less than or equal to probability of B. This is very obvious, right? And finally, inclusion exclusion property. Probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. If A and B are mutually exclusive, obviously this term is dropped, and we have a third axiom of probability. Okay, moving forward, we talk about the concept of conditional probability and Bayes theorem. We will use conditional probability in machine learning in the next topic, on Bayesian learning very frequently. So this is an important concept, and it allows us to update probabilistic models when additional information is revealed. For example, if you have two events A and B, and we want to find out probability of event A given event B, it simply means event B has already occurred. Right? So you are certain that if there is no uncertainty about event B. So event B has already occurred, and we want to find probability of happening event A, or probability of event A given event B. Right? So mathematically, it simply means so outcomes in A and B divide by outcomes in B. So previously, our set was sample space, but now we know that even B has occurred, and therefore probability of A given B would be the outcomes which are common in A and B divided by outcomes in B. This can be equivalently represented as outcomes in A and B divided by the total sample space, and I can write outcomes in B as so total divided by outcomes in B. Right? So this total would be cancelled with this total, and eventually you get what this is. But by definition, this is probability of A intersection B, and this is probability of B. And so we can write probability of A given B as probability of A intersection B divided by probability of B. Similarly, we can have probability of B given A would be probability of A intersection B divided by probability of A. And we know that probability of A intersection B is equal to probability of B intersection A, because intersection is a commutative operation. And if we note this, and we use these definitions, probability of A intersection B would be given by probability of A given B times probability of B, which is equal to probability of B given A times probability of A. So I have used so this one and this one to write this. And if I manipulate the terms, I get probability of A given B is equal to probability of B given A times probability of A divided by probability of B. So this is a very, very important result which we will use to develop an area of machine learning, what we call Bayesian learning. So this result is called Bayes theorem. So after Thomas Bayes. Okay, so how do you interpret this? So you know that event B has occurred. You want to find probability of event A given B has occurred. You can compute this by computing probability of B given A times probability of A divided by probability of B. Shortly in the next video, we will talk about the interpretation of this Bayes theorem. Or in the next slide, I will show you one example on how do we use Bayes theorem. But before we talk about example, I note the law of total probability. The probability of any event A would be given by probability of A given B times probability of B plus probability of A given B complement into probability of B complement, where B complement is sample space minus B. So B and B complement are mutually exclusive events. Obviously, you can extend this definition to multiple mutually exclusive events. If you have, say, m number of mutually exclusive events from the sample space, probability of A would be given by probability of A given A1 times probability of A1 plus probability of A given A2 times probability of A2, and so on and so forth, given A1, A2, AM, all of these events are mutually exclusive. Let's talk about one example utilizing Bayes' theorem. Okay, we assume that we have a very accurate COVID test, and information is that given that 0.008 of the entire population is positive, it simply means 0.8% of the entire population is COVID positive on average. And you have a very accurate test. The probability of correct positive prediction is 0.98. And the probability of the correct negative prediction is 0.97. It means if you are COVID positive and you go for a test, the probability of correct positive prediction is 0.98. And if someone is COVID negative, the probability of correct negative COVID prediction is 0.97. And we assume that a patient takes a COVID test and the result turns out to be positive. And we want to find the probability that the patient is not suffering from COVID, or if the patient is actually suffering from COVID. How do you find that? So if we just use the information we have here and we note the probability of correct positive prediction is 0.98, apparently it seems that you would say, since the test is very accurate, the patient is suffering from COVID. Well, let's find out this probability. So if we mathematically formulate the information we have, probability of COVID positive is 0.008, probability of COVID negative is 1 minus probability of COVID positive 0.992. Probability of testing positive given the patient is positive is 0.98, because test is 0.98% is correct with 0.98 probability. Probability that the patient is COVID negative and the test turns out to be negative is 0.97. Right? And if the patient is COVID negative, probability that test turns out to be positive, that is 0.03. That is 1 minus probability of test negative given COVID negative. Okay. Now let's apply Bayes' theorem. We want to find out what is the probability of test positive. And we know that using the law of total probability, we can write as probability of test positive given COVID positive times probability of COVID positive plus probability of test positive given COVID negative times probability of COVID negative. Because COVID positive and COVID negative, they are mutually exclusive events. So we can find this probability using these numbers. That turns out to be 0.0376. So what is this probability? That you randomly select a person and you test the person. The probability that the test turns out to be positive is very low, 0.0376. Right? Okay. We want to find out what is the probability that the person is actually suffering from COVID, given the test turns out to be positive. So using Bayes' theorem, we can write this as probability of test positive given COVID positive times probability of COVID positive divided by probability of test positive. So we have all of these values. Probability of COVID positive is 0.008. Probability of test positive given COVID positive is 0.98. And probability of test positive is, we have computed using law of total probability, 0.0376. If I substitute these numbers, and I get this probability, so 0.2085. So given test turns out to be positive, probability that the patient is suffering from COVID is very, very small. Okay. So this is not in line with our intuition, what we built earlier by reading the statement of the problem. And this is due to the fact that in the entire population, the probability of positive is very, very small, right? You only have 0.8% of the entire population is positive, sorry, yeah, right? This was a demonstration of the use of Bayes theorem to find conditional probability, right? Okay, moving forward, let's talk about the concept of independence. We say when the two events, uh, we have two events A and B, and if the two events satisfy this property, probability of A given B is equal to probability of A given B complement. We say A does not depend on B. So it doesn't matter whether B has occurred or B complement has occurred. The probability of A given B is equal to probability of A given B complement. So A does not depend on B. Mathematically, we can write this as probability of A intersection B divided by probability of B, and this can be written as probability of A intersection B complement divided by probability of B complement. So after some algebraic manipulations, and we obtain the final result, which is very, very important. Probability of A intersection B is equal to probability of A times probability of B. So on left hand side, we have probability of A intersection B. That means event A should occur and at the same time event B should occur. Right? And usually we refer to this as joint probability. Joint probability. So joint probability is equal to the product of individual probabilities. So this is the consequence of having two independent events A and B. Okay. So we should not confuse the concept of independence with the concept of mutually exclusive events. Mutually exclusive event means when A intersection B is equal to empty set. So when B, so we have an event B and we have an event B complement. So these are mutually exclusive events. So interpretation of independence between events, probability of A intersection B, we know that we can write it as in this form. And if we use the result we derived in the previous slide, probability of A times probability of B divided by probability of B, we get probability of A. So it simply means, how do you interpret this? It simply means probability of A given B is equal to probability of A. Probability does not change even if the event B has occurred, even if you have information that event B has occurred. Right? If A and B are independent events, obviously A complement and B, A and B complement, A complement, B complement, they are also independent events. And this can be shown very easily. We can extend the notion of independence for more than two events. If you have, say, AI, AJ, and AK are three independent events, the joint probability of these three events can be written as a product of individual probabilities. This is a very, very important concept. And this will form a basis of the naive Bayes classifier we will build, we will study in the next couple of videos. Right? So independence implies that if you have a joint probability, you can express joint probability as a product of individual probabilities. Okay. Mutual independence versus pairwise independence. Obviously, if you have events which are mutually independent, they will be pairwise independent, but and it's not the other way around. Okay, so that was these were some concepts about probability, some of the very basic concepts about probability, probability models, axioms of probability, Bayes theorem, and finally the concept of independence. Let's talk about the concept of discrete random variable. So first we see what do we mean by random variable. Random variable is a function which maps elements from the sample space to the real line. Random variables we denote by capital letters X or B, X or Y or Z. And we use small letters to denote the individual outcomes for random variable. So mathematically, our random variable X is a real valid function of each outcome of an experiment omega. Here we're assuming that outcome is discrete. So discrete random variable, a random variable that can take only a finite or countably infinite set of outcomes. It has to be finite, or it has to be, if it is infinite, it has to be countably infinite. That means you can count a set of outcomes. Okay, let's talk about some examples to understand the concept of discrete random variable. Say you have a random variable X of omega that corresponds to the number of heads if you toss 3 coins at the same time. What are the possible outcomes? You can have 3 heads, you can have 1 tail, 2 heads, you can have 2 tails and 1 head, or you can have all the 3 tails. So these are the possible outcomes. Sample space look like this. And if I define random variable, right? So random variable is mapping my sample space, right, to the real line. And I've defined random variable as number of heads. And this number of heads is an uncertain quantity, right? You can have 2 heads, you can have 1 head, you can have 3 heads. You can have no head. So each of the outcome of a sample space is mapped to a number in the real line, right? So we can define X of omega as 0 when you have no head, 1. So there are 3 outcomes correspond to X of omega is equal to 1. The 3 outcomes correspond to X of omega is equal to 2. And there's 1 outcome correspond to X of omega is equal to 3 when you have all 3 heads. Let's take one more example. A random variable that is equal to number of girls in a family of 4 kids. What are the possibilities we have? This is our sample space. So each outcome could be, you can have no girl, you can have 1 girl, you can have 2 girls, you can have 3 and 4 girls, right? So our random variable can take value 0, 1, 2, 3, and 4. So these are, for each of the outcome, we can define a value random variable we will take. Let's take another example. A random variable y, which is sum of the up faces of the 2 die. You roll 2 dice together and you sum of the up faces. That's the random variable. And this random variable can take any value from 2, 3, 4, and so on and so forth until 12. And obviously you can have for each outcome. So you can assign a value to the random variable y on the real line. Okay, so I assume now you have an understanding of a discrete random variable that maps each outcome in your sample space to the real line. We talk about the concept of probability mass function. So probability mass function for a random variable, it assigns probabilities to the individual outcomes. For a discrete random variable x, we define its probability mass function as that if xi is your outcome on real, sorry, is your mapping on real line, what is the probability that a random variable x would be equal to the value xi. So this is the value of probability mass function for a given xi. And by axioms of probability, we know that this, since probability would be always between 0 and 1, so we expect probability mass function would be between 0 and 1, and obviously the sum of all probabilities it should be equal to 1. That means probability of sample space is equal to 1. So when you sum all the probabilities, so you have you get a sample space. For examples we discussed, let's define probability mass function. So for example, in which we had number of heads, if 3 coins are tossed at a time, let's say this random variable is x of omega. Probability that this random variable takes a value is equal to 0 would be given by probability that you get 3 tails, which is 1 over 8. Similarly, one head 3 over 8, 2 heads 3 over 8, and similarly all heads is 1 over 8. We also plot this probability mass function versus all of the values a random variable can take. Right? A random variable can take 0, 1, 2, 3. Right? And what's plotted here is the probabilities that a random variable can take value is equal to 1. So this number 3 over 8, probability that a random variable x takes the value 1, and so on and so forth. And if you sum all of these, 1 over 8, 3 over 8, 3 over 8, 1 over 8, this sum should be equal to 1. And also each of these probability should be non-negative. It can be 0, but it cannot be negative. Okay, for example, in which we use random variable to denote number of girls in a family of 4 kids. Right? So we get 1 over 16, 4 over 16, and then we have 6 over 16, 4 over 16, and 1 over 16. You can confirm this from the table we saw earlier. If I ask a question given this probability mass function, and if you want to answer these two questions, what is the probability of exactly 3 girls in 4 kids? That would be simply you can read this value from the probability mass function plot. That is 4 over 16. Right? What is the probability of at least 3 girls in 4 kids? You can have 3 girls or you can have 4 girls. That is 4 over 16 plus 1 over 16. That is equal to 5 over 16. Okay. So I assume now you have understanding of discrete random variable and probability mass function. Let's talk about some important discrete random variables. The most simplest, in fact, the simplest random variable we can have as a Bernoulli random variable. If there are only 2 outcomes of an experiment, the experiment is modeled with uniform random variable. For example, tossing of a coin. So we use one variable theta to define probability mass function of a Bernoulli random variable. So we say a random variable when it takes a value is equal to 0, probability is theta, and when it takes value 1, you get 1 minus theta. So only one single parameter theta can characterize the probability mass function of a Bernoulli random variable. Another commonly encountered discrete random variable is a uniform random variable. If the outcomes of the experiment are finite and are equally likely. Right? So you have n outcomes and each outcome is equally likely. So probability of each outcome would be 1 over n. And obviously noting this, we can have this probability mass function. That you have probability of outcome 1 is equal to 1 over n, probability of outcome 2 is also to 1 over n, and so on and so forth. For each of the n outcomes, probability of each outcome is equal to 1 over n. We also note a Poisson discrete random variable. Right? A random variable x is said to have a Poisson PMF, and that is defined by parameter lambda if Poisson satisfies this definition of probability mass function. So this PMF is characterized by a variable lambda. And we use Poisson random variable to model uncertainties in many physical phenomena. For example, arrival of photons in a telescope or distribution of nodes in wireless and sensor networks. We model it using a Poisson random variable. Telephone calls arriving in a system or arrival of network messages in a queue of transmission. So and when we have counting or counting phenomena, we usually use Poisson variable to model it. Okay, multiple random variables. When events are defined by more than one random variable. So say we assume that we have x represent one variable and say y represent another random variable. And x maps element of a sample space to a real line, and y also map elements of a sample space to a real line. But this mapping can be different. Then we can define the event involving both x and y as that x belongs to B and y belongs to C. And this is interpreted as x of omega belongs to B and y of omega belongs to C, right? So the important information here is we have this and here. Or it simply means the event that x belongs to B and y belongs to C. This is a very, very important concept. This is a joint probability. Right? The event above is a function of two random variables, and it is comprised of only those points on the real line that are common between B and C. So x belongs to B and y belongs to C. It simply means x belongs to B intersection y belongs to C. So we can find the probability of multiple random variables or such events by introducing the concept of joint probability. Joint probability involving two random variables is given by probability of x belongs to B and y belongs to C is equal to probability of x belongs to B intersection y belongs to C. Interpretation is that these two, the random variable x belongs to B and random variable y belongs to C. For such an event, we can define, this is important, joint probability mass function. Right? And it is defined, we call it joint because it depends on both x and y. And interpretation is, so pxy, xi, yj. So this quantifies the probability that a random variable x is equal to xi and the random variable y is equal to yj at the same time. Okay. For a joint probability mass function, we define marginal probability mass function. In fact, we can recover, given joint PMF, we can recover individual PMFs by averaging out the other random variable. For example, from this joint PMF, we can recover probability of PMF of random variable x as average joint PMF or some joint PMF for different values of the other random variable y. Right? And similarly, we can recover probability a mass function of y from the joint probability by averaging out the random variable x. Okay. So assume now you know the concept of joint probability. Okay, let's connect the concept of joint probability with the concept of independence. When the two random variables are independent, when they are independent, we can write the joint probability as a product of individual probabilities. We have seen this earlier, right? This follows from the notion of independence. And similarly, we can extend this and we can write the joint PMF as a product of individual probability mass functions when we have independent random variables. When the two random variables are independent, the joint PMF is equal to the product of the individual PMFs. Right? And obviously, we have presented here for two random variables, and we can extend for multiple random variables. And we will extend this when we define, when we assume, when we carry out naive Bayes assumption in designing a Bayes optimal classifier. Okay. Let's talk about very briefly concept of continuously random variable. As the name suggests, a continuous random variable is one for which the outcome can be any value in an interval of the real number line. For a discrete random variable, it maps, it assigns the outcomes to discrete values. But here, a random variable can take any value in the interval of the real number line, or it can be the complete real number line. There are always infinitely many sample points in the sample space. For discrete random variables, only the value listed in the probability mass function have positive probabilities. All other values have probability 0, right? So on real line, you only have discrete values on a real line. But for a continuous random variable, we can have outcomes can be any value in an interval or in the whole real number line. For a continuous random variable, the probability of every specific value is 0. Probabilities only exist for an interval of values or for a continuous set of values. When we talk about continuous random variable, we don't compute that a random variable takes a value is equal to some value. Instead, we're interested in that what is the probability that a random variable y can take values between a and b. So it's an interval defined, open interval in fact, between a and b. For a continuous random variable, probability of y is equal to 0, as I said earlier. We do not compute probability for a specific value on real line. That's always done out to be 0. For a discrete random variable, we had probability mass function. For a continuous random variable, the counterpart is probability density function. And usually it's on a continuous scale. So y is continuous, and this is probability mass function for the random variable y. And if we're interested in finding out the probability that a random variable y can take values between a and b, so if a and b is this interval, So we can compute the area underneath the probability mass function, sorry, the probability density function between A and B. So to find probability that a random variable y can take any value between A and B, we integrate probability density function from A to B. For example, in this case, it turns out to 0.4. The PDF denotes a curve against the possible values of a random variable, and the area under interval of the curve is equal to the probability that random variable is in that interval. Right? And yeah, for this example, we can compute this as probability of random variable is between A and B as area under the probability density function, which is also called PDF. Okay, very briefly, PMF versus PDF. For discrete random variable, we have probability mass function, and the PMF looks like a bunch of spikes because we only have probabilities defined for discrete values. And the probabilities are defined by the height of those spikes along real line. For a constant random variable, we have a density function. And this density function looks like a curve, and the probabilities are represented by areas under the curve. Right? So for a discrete random variable, we have PMF. For a constant random variable, we have a PDF. A bunch of spikes along real line, a continuous function, a curve, it's like a curve along real line. You compute probabilities by just noting the value of the spike. Here, in a continuous case, we compute probabilities by integrating this PDF, by computing the area under the PDF over the interval. Okay. So some of the characteristics of PDF, and they simply follow from axioms of probability. Obviously, we require PDF to be greater than or equal to 0. And when you integrate PDF from -infinity to infinity over the whole real line, since sample space is a Shor event, this should turn out to be 1. Okay, some important continuous random variables. Uniform random variable, which we use to model experiments in which outcome is constrained to lie in a known interval, say AB, and all possible outcomes are equally likely. So we say we have a uniform random variable that follows a density uniform AB. It simply means a random variable can take any value between A and B, and each value is equally likely. And this PDF is given by when random variable x is between A and B, the value is 1 over B minus A. So this is indeed the width of the interval. Right? And so use 1 over B minus A to ensure that when you integrate this from -infinity to infinity, the total area should be equal to 1. And when the random variable is outside the interval, the value of PDF is 0. So we can plot this PDF. But when this is between A and B, you get 1 over B minus A. When this is less than A, PDF is 0. When X is greater than B, the PDF is 0. And obviously you can check this when you integrate from -infinity to infinity, it is equal to 1. So another important random variable is exponential random variable, and which we use to model lifetimes. For example, how long it takes before next phone call arrives, how long it takes a computer network to transmit a message, how long it takes a radioactive particle to decay, and so on and so forth. So we use a single variable lambda to characterize PDF. So we define PDF for lambda greater than or equal to 0. So when X is positive right? It's a piecewise PDF with lambda x minus lambda x, right? And when x is less than 0, you get 0. And this piecewise, you see you're gonna jump x is equal to, at x equal to 0. So this PDF is only defined for x greater than or equal to 0. For x less than or equal to 0, the value of PDF is equal to 0. Right? For larger value of lambda, you get a higher spike at 0, and that decays to 0 quickly, as compared to when lambda is equal to for smaller value of lambda. Okay. Most important random variable widely used. In fact, we will see it. We use it in tons of applications. A Gaussian random variable. Right? Some people refer to it as a normal random variable, or they refer to its PDF as a bell curve. So this is PDF is parameterized by two parameters. One is called mu, which is mean, right? And sigma square, which is called the variance of a random variable. And we define mathematically PDF in this form. We have normalization by 1 over sigma 2 pi. This normalization ensures that when you take integral of PDF from minus infinity to infinity, you get 1. And the distribution along x is given by this exponential raised to the power minus x minus mu whole square divided by 2 sigma square. If you try to interpret this mathematical definition, so we have x minus mu square. It indicates that the distribution is symmetric around mu. And this sigma square is capturing the spread, is characterizing the spread of your curve. So mu is called the center or mean, and mu can be any real number. And standard deviation is sigma. So sigma square is the variance. And this standard deviation, it defines the spread. It quantifies the spread of the distribution along around the center. Right? So this is x here, and mu is the center of the distribution. And when sigma is equal to small, for smaller value of sigma, you get a more peaky curve and less spread relative to when sigma is equal to large. Right. So this was a Gaussian random variable. When mean is equal to 0 and standard deviation is equal to 1, we refer to this PDF as the standard normal density. Right? This random variable is called standard normal random variable. This was a very quick overview of some of the very basic concepts related to probability theory. We will define more concepts as we progress in the course, as we encounter, as we feel the need to define those concepts. We'll stop here, and in the next video we'll start with the Bayesian learning. Thank you.